the first thing I was going to do today was I had a couple people email me because I did not go over the integrals of the inverse trig functions. And so that's what I was going to start with, was just going over the intervals of the inverse trig functions. And if anybody has any questions, then I'll take them. And then we'll do section 8.4, which is what I plan to cover today, which is about integration by parts. So that's kind of the game plan for today. So the inverse trig integrals. So inverse trig integrals. Okay. So if you have the integral of 1 over the square root of 1 minus, or actually, I'm trying to think, how is it usually written? It's a squared. Whoops, I pulled the wrong sheet out here. Give me 1 second to pull the correct sheet up here, because I want to write it the way most of the books write it. Because I usually think of it as the a squared, but that's not what it is. So give me 1 second to find the page I'm looking for here. Here we go. Okay. So 1 over I thought I had this all pulled up before I logged back on. I was like, oh yeah, let me pull this up so then it's right here. And of course, no, it's not. 1 second. Okay, there we go. All right, so nope, that's still not the page I'm looking for. I know you guys are like, what is she doing? And that's what I want to say. Yeah, what am I doing here? Because I have it. There's a way I like to write them, and of course, I can't find it right this second. But this is what, yeah, it is, it does have, sometimes it has a U. I usually write it with an A, and it just, okay, there we go. I found it. All right. So, it's just they were split very nicely in one of my books, and this book is just not one of them. Okay. All right. So, square root of a squared minus x squared is equal to the inverse sine of x over a plus c. The integral of 1 over the square root of x squared minus a squared is give me where I know I'm going to explain why this is so hard for me to do here in a second. Oh, here it is, yeah, with an X here out in front. So this is 1 over a inverse secant of the absolute value of x over a plus c. And then the integral of 1 over a squared plus x squared is going to be the inverse tangent of x over, 1 over a, the inverse tangent of x over a plus c. Did I drop the 1 over a? No, I didn't. Okay. All right. So obviously, right, is that d dx? Oh yeah, there should be a dx on the end of these, of all of these. Yeah. Okay. So why is Dr. Gorman fumbling with these so much? Is because Dr. Gorman actually doesn't like to memorize these. And so Dr. Gorman doesn't memorize them this way. Dr. Gorman actually just uses trig substitution, which is one of the techniques that we're going to learn later on in the course. So it's about, I think it's like the second or the third thing we're going to learn after that first test. So that's why I don't have these committed to memory. I have like the basic ones. So like 1 over 1 plus x squared, right? So I personally know that like the integral of 1 over 1 plus x squared dx, that's inverse tangent, right? So this is the inverse tangent of x dx. I know the integral of 1 over x square root of x squared minus 1 dx is the inverse secant of the absolute value of x plus c. And I know that the integral of 1 over the square root of 1 minus x squared dx is inverse sine of x plus c. So, depending who you had for Calc 1, they might have made a big deal out of inverse trig integrals, and they might not have. They might have made you do a whole bunch of algebra to get things like into this form, and they might have even done them with u's instead of the a's, and the U-Substitution, and all that jazz. And that's just like not my jam, because I really love trig substitution. And so if you give me an integral that's not straight up one of these, I'm going to do trig substitution on it. And that's just me. So I don't really like to necessarily memorize these guys, but you can. So if I were to put something on the first test that had an inverse trig, it's going to be exactly one of these three, right? So it is possible I might put 1 over 1 plus x squared, and then it's, and that should not be a dx. You guys didn't call me on that. This should be a plus c. So it's possible that I might put something like one of these on the first exam, but outside of like these exact three integrals, I am not going to put any inverse trig on the exam, just because I like the trig substitution, which we're going to get to later on. So that's kind of my little like talk about inverse trig functions. So with that being said, does anybody have any questions before we go into what I'm going to teach you today? No. It's always weird because I can't see. This is the only thing I don't like about. Can I go over f on the integrals? From the in-class sheet or from the, so let me see. Yes, I should say, yes, I can go over whatever f it is you want me to go over, but I just want to see which one. From the in-class review problems, or, okay, from the Calc 1, so let me see if I get the right problem. You can tell me if it's the right problem here in a second, the handout. So f, the integral from 0 to pi over 4 of 4 cosine 2x dx, that one? Okay, sure. So this is from the this is from the Calc 1 review. And actually, let me go to the next page just so that we have enough room. I think I can fit it down here, but just in case. So what I'm going to end up doing so that we make sure we kind of have all of the recording is every time I change a page, I'm going to stop the recording and then I'll restart the recording. So it might look like I'm not recording the whole entire thing, but I definitely am. So don't worry about it. Okay. So Calc 1 review. Sheet. So part F gives us the integral from 0 to pi over 4 of 4 cosine 2x dx. Okay, so there are two ways you could do this problem. So one way you could do this problem is by using U-substitution. The other way is by using that kind of shortcut that I talked about how I used. So which way do you want me to show you? Do you want me to show you the U-substitution? You want me to show you the shortcut? You want me to show you both ways? Which way? Both. Okay. So let's do the U-substitution part first. So if you look at this, we have an inside function. It's this 2x. So if I did the U-substitution, I would let u be equal to 2x, which means du is going to be 2dx. Does that make sense so far? Okay. And then I need a 2. So this part here is going to become my u. I have the dx, right? The dx here matches with this dx, but I need a 2. So I'm going to put a 2 on the inside, but that means I need to put a 1/2 here on the outside. So now this 2 and the dx, this part is all going to become the du. And then the other thing I'm going to do is I'm going to change my limits. So when x is equal to pi over 4, u is equal to 2 times pi over 4, or pi over 2. And when x is equal to 0, u is equal to 2 times 0, or 0. So questions on any of that so far? Okay. So this integral is going to turn into the integral. So I have a 1/2 outside here. I have the integral instead of, so 0, the 0 here matches up with this 0. So the bottom number here is 0. The pi over 4, this pi over 4 matches here, which is going to be the pi over 2. So that stuff, that's what's going to happen there so far. And then I still have a 4 sitting in here, and then I have the cosine of u du. And I could pull that 4 out in front. So this would be, is the 4 part of the cosine 2x? So it's 4 times the cosine of the 2x. So the 4 is just a constant that's sitting out front there, which is why I'm now going to pull that 4 out in front of the integral. So I can multiply this 1/2 times this 4 and it gets me 2 times the integral from 0 to pi over 2 of the cosine of u du. Does that make sense to people? Did I answer questions about the 4? Yeah, so that's exactly what I did, but I took a second step to do it. So I probably was doing that as you were typing your question, Robert. Yeah. Yeah, one of the things of weird things about the online environment, right? Okay, so now we're at this point, and so I just have to figure out first off, what is the integral of the cosine of u? So what did we say the integral of cosine of u is? Okay. Yeah, so all right. So we've got somebody saying sine and we've got somebody saying cosine, or we've got somebody saying negative sine. So let's think about what's the derivative of sine? Yeah, so the derivative of sine is cosine, which means the integral of cosine would just be sine. So this is just 2 sine u evaluated from 0 to pi over 2. And so then we're just going to plug in those limits of integration. So this is going to be 2 sine of pi over 2 minus 2 sine of 0. So the sine of pi over 2 is what? Whoops. Anybody remember what the sine of pi over 2 is? No. Okay. So there's a couple, yeah, 1. Right, exactly, it's 1. So there's a couple points it's going to be immensely helpful to you if you remember your unit circle. At least a little bit, right? In particular, the 4 cardinal points here, I kind of call them. So these 4 points, so if you remember, this is 0, radians. This is pi over 2 radians. This is pi radians. This is 3 pi over 2 radians. And so since I have a circle of length 1, right, this is the point 1 comma 0, 0 comma 1, minus 1 comma 0, 0 comma minus 1. And so the thing to remember is that the sine is the y value and cosine is the x value. So if I'm looking for the sine of pi over 2, I'm looking for the y value because sine is the y value, and so it's a 1. So this is going to be 2 times 1 minus 2 times the sine of 0 is going to be 0. So this is just going to end up being 2. So does that make sense first before I show you my shortcut way? Yeah, the sine is the y value on the unit circle. Yep. And then tangent is y over x. Yep, exactly. So cosine is x, tangent is y over x. No problem. Okay, so my shortcut way, which I can't remember how I did it in the answer key. I might have done it the shortcut way. So remember, I showed you last time the shortcut way. If you have the integral of the cosine of ax dx, that is going to end up being 1 over a sine of ax plus c. So that was the shortcut rule that we talked about last time. So I can use that shortcut rule on this original problem. So my original problem was the integral from 0 to pi over 4 of 4 cosine of 2x dx. So the first thing I could do, if I want, you could do it all in one step, but if you wanted to take 2 steps to do this, I would factor out the 4 first. So this is going to be 4 times the integral from 0 to pi over 4 of the cosine of 2x dx. And then this matches up with my problem over here, right? So that's my 2, that's my a. So this is just going to end up being 4 times 1/2 the sine of 2x. And in this case, I don't have plus c. I'm evaluating between 0 and pi over 4. And again, I can multiply that 4 times the 2. So I have 2 sine of 2x evaluated from 0 to pi over 4. So all I'm going to do is plug in pi over 4. So 2 sine of 2 times pi over 4 minus 2 sine of 2 times 0. So you're going to see I end up with the same exact place. 2 sine of pi over 2 minus 2 sine of 0, which just like before is 2 times 1 minus 2 times 0, or 2. So I personally use this, and I usually don't even write this step or this step. I kind of jump right from here to here. Just because in my head I'm like, oh yeah, I'm going to get a 1/2 out, and it's going to 1/2 times 4 is 2. So I just go right from here to here. And so the reason I do that is because it's shorter, right? I didn't have to find the u, I didn't have to change the limits, I didn't have to do all that stuff. And so that's kind of how I do that problem. Does that help? Awesome. Any other questions? So I'm assuming that's I, right? So yes, I can, yep, I can totally do I. So start again. Okay, so I, whoops, is the integral of x e to the x squared over 1 plus e to the x squared dx. Okay. So I look at this problem and I go, well, this is not one of just the straight up integrals that I should already know. So right now, right, which is pretty nice, you either have to do a little bit of algebra, but this isn't something that algebra is going to help us on, or it's a U-substitution. So I'm right off the bat going to kind of look at this and go, ugh, that's a mess. It's probably a U-substitution because it's the only rule I got going on. So what I'm going to do is, in terms of a U-substitution, one of the first things I try in a U-substitution, if I have a fraction, is I try to make the bottom of the fraction be the U. So if we think about it, we're going to try letting all of this stuff be U and see what happens, okay? So I'm going to let U be equal to 1 plus e to the x squared. And now I need to take the derivative of that. So the derivative of 1 is 0, so that goes away. The derivative of e to the x squared, so I have e to a bunch of stuff, so it's going to be e to that stuff, so e to the x squared, times the derivative of the stuff. And so the derivative of x squared is 2x, and then I have that dx. Does that make sense so far? Okay. So if I look at this, right, I already said this bottom we made u. If I compare the things I need, so I need a dx, I have a dx. I need an e to the x squared, I have an e to the x squared. I need an x, I have an x. I need a 2, but that's what I'm missing. So I'm going to put a 2 in, which means I just need to balance it on the other side with the 1/2. So this whole top part times the dx, this now becomes du. So this ends up being 1/2 times the integral of 1 over u du. And does anybody remember what the integral of 1 over u du would be? I feel like this is where virtual class is. Yeah, natural log of u, natural log, if you said natural log of x, yeah, you're thinking the right thing. I was going to say, this is where it's weird, right? Because I ask a question, and then I have to just sit and wait, and, for you guys to type it in. So this becomes the natural log of the absolute value of u. So this is going to be 1/2 the natural log, the absolute value of u, plus a constant. And then all I have to do is plug back in for u. So we'd have 1/2 the natural log, the absolute value of 1 plus e to the x squared plus c. Now, in this particular case, if you wanted to drop the absolute value signs, you could, because e to the x squared is always going to be positive and 1 is always positive. So you could replace the absolute value signs here with parentheses, but you don't have to. I'm fine with just leaving the answer like that. So that's the answer to I. Does that help? Great. Any other questions? Can I go over the U substitution part? Sure. Like how I picked the U, or when I found like the DU part, or like all of the stuff about the U substitution? The DU part. Okay, sure. So, excuse me. What I'm doing is, so we picked this bottom part here, the 1 plus e to the x squared, to be the u, right? So I write that down. And then I have to take the derivative. So down here, what I really have is I have e to a bunch of stuff. So when I take the derivative of 1 is 0. So that part goes away, and I didn't write anything. So I just have to worry about taking the derivative of this. So we talked about last time, if I have e to a bunch of stuff, the derivative of e to a bunch of stuff is e to the bunch of stuff times the derivative of the stuff. So I have e to the bunch of stuff, so e to the x squared, times the derivative of the stuff. And so the derivative of x squared is 2x. And then I have that dx part. Does that help? Great. Other questions? No problem. Okay, so problems like what was on that review sheet, and the other extra problems I put up there on Canvas, those are all like good problems, and so the problems on the test might, would be kind of comparable in the difficulty level, I should say. At the end of class today, before we end class today, I'm going to actually talk about the test, talk about the homework and stuff like that. So I'll share my screen and show you some things on Canvas for both of those things. So then the other thing we're going to do today is we're actually going to talk about section 8.4, and section 8.4 is integration by parts. So this is section 8.4. Integration by parts. And we are jumping around a little bit in the textbook in chapter 8 here. Right, I didn't start with section 8.1. I just like to teach integration in a certain order, and so I rearranged the sections of this book to be more in line with how I teach integration. Okay, so when we integrate, right? So far, if we want to integrate something and it's not just one of the basic integrals that we know, the only thing we know how to do is U-substitution. So integration by parts is going to be used for integrals that have a certain, that look a certain way. So it's used for integrals of the form, you have some function f of x times some other function g of x dx. So it basically, what it does is it is essentially, it's tied into the product rule. So it is basically when you were given something in Calc 1 and you took the derivative of it using the product rule, this is essentially undoing the product rule. And it's especially useful when one of your functions you can easily take a derivative of, and the other function you can easily integrate. So kind of the way I write it, since my functions here are generic, I usually say it's especially useful when f of x is quote unquote easy to differentiate and g of x is easy to integrate. All right, now I put the word easy in quotation marks because, like, you still might need to use a U-substitution to integrate something, but that's still technically easy to integrate. Whoa, what happened here? Did I freeze again? Can you guys still hear me? Because I can't see me anymore. So, okay, wait a minute, let me... Okay, so as I was saying, it's easily integrated. So the integration by parts undoes the product rule. So I'm going to show you where integration by parts comes from. You are not going to have to repeat. Yeah, now it's recording. So awesome. But thank you for reminding me. So you, integration by parts, undoes the product rule, and I'm going to show you where it comes from. You are not going to have to like repeat back to me where it comes from, but I just want to show you so it doesn't look like I pulled the integration by parts out of thin air, right? So I could just give you, hey, here's the formula for integration by parts, but it's going to look like I just magically knew what this formula was. So I want to show you where the formula for integration by parts comes from. But then after I show you the formula, we'll write down kind of like the main key point. Like this is the thing you need to take away and the thing you need to remember, okay? But I do kind of want to show you where it comes from. So it undoes the product rule. So to show you where it comes from, we're actually going to start with the product rule. So let's say that we have the function f of x times g of x, and I want to take the derivative of that with respect to x. So we talked about the product rule last time, right? So we said that the product rule is the first function times the derivative of the second, plus the second function times the derivative of the first. Do you guys remember us talking about that last time? Okay, so I'm going to write that out in terms of my f and my g. So it's the first function, f of x, times the derivative of the second function, which we're just going to call g prime of x, plus the second function, g of x, times the derivative of the first function, which is f prime of x. So all I've done is just written out what the product rule is. Are we okay with that? Okay. So now that I have that, I'm actually going to go through this whole entire equation, and I am going to take the integral of each of these pieces. So there's three main pieces there. I have like the left-hand side and then two pieces on the right-hand side. And so I'm going to take the integral of each of those pieces. So the integral of the derivative with respect to x of f of x, g of x, dx is going to be equal to the integral of f of x, g prime of x, dx, plus the integral of g of x, f prime of x, dx. So all I've done so far is I started with the product rule, I wrote down what the product rule was, and then I have an equation that involves the product rule, and I just took the integral of every single piece. Any questions on anything I've done so far? No? Okay. So now, in this first piece here, I have a derivative, I have an integral of a derivative. So if you remember back to Calc 1, integrals and derivatives, they undo each other, right? So like if I start with x squared and I take the derivative, I would get 2x, but then if I integrate, I get back to x squared, right? Plus a constant. But so basically if you have a derivative and an integral, or an integral and then a derivative, they're just undoing each other. So all that's happening here on the left-hand side is this integral followed by the derivative of this just undoes everything and leaves us back what we started with, which we started this whole entire problem with just, oh, I have f of x times g of x. So f of x times g of x is actually equal to the integral of f of x g prime of x dx plus the integral of g of x f prime of x dx. Questions? No. Okay, so I'm now just going to rearrange my terms a little bit. I'm actually going to take this term here, and I'm going to move this term to the other side. So we're going to have f of x, g of x, minus this whole integral, the integral of g of x, f prime of x, dx, equals the integral of f of x, g prime of x, dx. And so essentially what I have here is actually what is integration by parts, the integration by parts rule. However, usually when we talk about integration by parts, we don't talk in terms of f's and g's. We talk in terms of u's and v's. And so what I'm going to do is I'm actually going to rename some things. So we're going to call f of x u. So this would be u. This here would be u prime. But when you put u prime along with dx together, this actually becomes du. So it's that differential. And then again, this is u. And then g of x, we're going to call v. And then again, this same integral here, when I have g prime of x dx, we're going to call that dv. So finally, the integration by parts rule. So integration by parts says, so I'm going to do two things here. I'm going to rewrite the rule just in terms of those u's and the dv's. But to make it actually look the same way we usually see it in textbooks, I'm going to actually flip-flop my equation. So instead of writing this side first and then this side second, I'm going to write this right-hand side first. So this is going to be the integral of u dv is equal to uv minus the integral of v du. And so all I've done here is I've just rewritten this line here in terms of u's and v's. So this is the important thing that you need to remember. So if you're given a problem and it's not, so when I go through problems, I look at them and I go, well, can I just regularly integrate it? Yes or no? If the answer is no, could I do a little bit of algebra? Yes or no? If the answer is no, is it a U-substitution problem? And if the answer is still no, then I go, well, does it look like an integration by parts problem? Does it look like two pieces multiplied together? So that's kind of my thought process. You're going to see that when we're doing problems here in a minute. So that formula, that's the most important thing. You don't have to worry about all the other stuff that's on this page. It's just showing you where this formula comes from. But this is where that integration by parts formula comes from. So let's do an example so that we kind of see what I'm talking about in action. And then if people have questions, you can let me know. I'm just going to copy this so we can take it with us to the next page. Okay. So, go leave that right there. Okay, so here's our integration by parts formula. So for example, we're going to do a bunch of examples here. Integrate. So example A, we're going to have the integral of x e to the x dx. So if I look at this problem, if I look at this problem and the first thing that happens is I say, okay, it's not something I just know how to integrate. I know how to just integrate x. I know how to just integrate e to the x, but not when they're multiplied together. And then you might go, well, maybe it's a U-substitution. But if you tried any U-substitutions here, you're going to quickly find out that it doesn't really make anything better for you. So the thing I'm going to notice is that it kind of looks like I have two things multiplied together, right? I have an x and I have this e to the x with the dx. So I am going to use integration by parts. And the thing that I want to identify is a u and a dv. So when you do integration by parts, you're taking, so remember here I have my original part is a u and a dv. So I need to break this problem into a u and a dv. And I said you want u to be easy to differentiate and e to be easy to integrate. A lot of times we want u, if we can kind of make the u get, like, I hate to use the word smaller, but kind of get simpler. as we go through it, as we take a derivative, that's helpful. So if you think about x, if I take the derivative of x, I just get 1. And 1 is simpler than x. So we're going to try letting x be our u, and which means everything else here would be our dv. So if I write that down, u is going to be equal to x, dv is going to be e to the x, and I have to take the dx part with it. So the first thing I'm going to try to do is split up my integral into that u part and the dv part. And in a minute, when we're done with this problem, I'm going to give you a little bit like a mnemonic to kind of help you at least get a starting point for what to pick for your u and your dv. Questions so far? Okay, so I want to plug into this formula. So to plug into this formula, I'm going to need to figure out what v is, and I'm going to need to figure out what du is. So if I have u equals x, to find du, I'm going to take the derivative, just like we did in U-Substitution. So I said the derivative of x is 1, so this is going to be 1 dx, or we can really just write that as dx. And then to find v, I have to integrate. So v is going to be equal to the integral of dv, so the integral of the stuff above it there. So it's going to be equal to the integral of e to the x dx. And what's the integral of e to the x? Yeah, e to the x. Okay, now you might say, well, it's e to the x but plus c. Yeah, it is usually e to the x plus c. When we're doing this little middle step here, we're not going to worry about the plus c. You could put a plus c here, but then as you go and do more on the problem, you're going to kind of basically wind up with multiple plus c's, and so it's just not worth it. We'll just wait till the very end and collect all the constants together then, and just put one giant plus c at the end of our problem. So this now is going to be equal to, so remember, we're looking at uv minus the integral of v du. And so that's what I'm going to want to plug in here. So u is x, v is e to the x, minus the integral of v e to the x times du, and du in this case happens to be dx. So I happen to get something that I now actually can integrate. So this new integral here is an integral that I actually can integrate. And so now I'm actually going to do that integration. So this is going to become x e to the x minus, we said the integral of e to the x is e to the x, and so then we have plus c. Okay, so let me see. What is the du? So du here, so du is dx, but it's not always dx. It's the derivative. So remember, here I have u is equal to x, and I'm taking the derivative of this. So in this particular case, we're writing the derivative as that differential. So I start with u, derivative on this side becomes the du, derivative on this side. The derivative of x is 1 times dx, and so that's how we just get dx. Does that help make that clear? And we're going to do more problems, so it'll probably become even more clearer as we go. Great. Other questions? No. Okay. So, which one did you say should be easy to take? Okay, u should be, okay, why is v du only e to the x dx? Okay, so u should be the thing that's easy to take the derivative of. So basically, I'm looking at my original problem here, and you might say, well, e to the x is easy to take the derivative of. Yeah, e to the x is. But if I picked e to the x as u, when I did dv, I had an x, and then I would end up getting an x squared, so it's almost like I'm making my problem worse. So you're looking for something that's easy to take the derivative of, so in this case x, and something that's easy to integrate. So e to the x dx is why I picked, because I know how to integrate e to the x dx. It's just the same thing. So why is v du only e to the x dx? So remember, I'm taking my original problem, I'm splitting it into two pieces. So I split it into these two pieces. So the first piece here was my u. So this is one piece. That becomes my u. This second piece here, this became my dv. So it's basically I have to split my integral into a u piece and a dv piece. Does that help, David? Other questions? Oh, yeah, I can see that. Yeah, it's easy because you want to, yeah, you got to be a little careful with the V's and the U's. No, it's okay. It happens to lots of people. So as you guys kind of are asking me questions, you might guess that like one of the hardest things is to figure out what should I pick for you? Like how did you know you should pick X for you? So I have something to help decide what to pick for you. So to help decide what to pick for you. So I use the an acronym LIATE, or LIATE, depends how you want to pronounce it. LIATE. And this tells you the order of to pick for you. So you start on the left part of the word, and then it like, see, do I have any of those? I'll pick that for my U. If not, move on to the next thing, on to the next thing, on to the next thing. So the L stands for logarithms. So if you have a logarithm in your problem, you pick that to be the U. The I stands for inverse. So if you had like an inverse trig function or something like that, you would pick that for the U. The A stands for algebra. So algebra, so like, I know you're like, what do I mean by that? So basically, when we say algebra, we're kind of talking about algebraic functions, and they're mostly things like polynomials. So when I picked X, I picked that because I started to go through this and I was like, oh, do I have any logarithms in this problem? No. Do I have any inverses in this problem? No. Algebra, do I have any polynomial parts in this problem? Yeah. X. X is a polynomial. It's just a linear function. So that I should pick as my U. T is for trig functions. So followed by algebraic functions. The next thing you would pick would be trig functions. And then the very last one is exponential functions. Now, this isn't like set in stone rule, okay? It's possible there's a problem where you might pick an exponential function for you over something else. But in general, this rule holds pretty true, especially for the problems we're going to be practicing. So that's going to help us kind of pick what should I pick for you. So should we try another one? I mean, I figure you guys probably want more examples than just one before I'm like, yeah, go do the homework, right? Okay. So let me, that way we kind of have them together to reference. So, and you should have them in your notes and stuff like that. And we have them bigger on the other screen, so I'm not too worried about the fact that they're small. Okay, so B, we have the integral from 1 to 2 of the natural log of x dx. Okay, so if you think about it, I know natural log of x looks like a just easy, simple little function. But again, it's a function we don't know how to take the derivative of, or how to take the integral of. It's not one of the main ones we went over last class. And there's not really anything in terms of U-substitution. Like, what am I going to substitute for? Like, I can't. So this is a good candidate for integration by parts. And so if we look at that laete, right, the very first thing says, you know, things I should pick for you, logarithms. Do I have a logarithm in this problem? Yeah, I have the natural log. So natural log is a form of a logarithm, right? So I am going to let my u be the natural log of x. So if we think about that, I've made this part u, which means the only thing that's left is dx. So in this case, dv just so happens to be just plain old dx. And that's okay. That can happen sometimes. This is one of the powerful things about integration by parts, is it can help you integrate things that otherwise you kind of wouldn't be able to. Okay, so I have u equals the natural log of x, and so now what I want to do is I need to figure out du, and I also need to figure out v. So du, so what's the derivative of the natural log of x? Okay, 1 over x, and then we're talking about a differential here, so it's going to be 1 over x dx. And then from the dv, we're going to want to integrate, so v is going to end up being the integral of dx. So you might go, ugh, that's kind of weird. But the thing you just want to remember, if you just have the integral of dx, it's like you have a 1 here. So what's the integral of 1 dx? Yeah, x. So this just ends up being x. So I have all the pieces I need so far, right? I have u, I have v, I have the v and du, right? All the pieces I need. So this is going to be uv, so the natural log of x times x, minus the integral of vx du, which is 1 over x dx. Now, you'll also notice I'm being a little sloppy in that my original problem had limits of integration, and in the end here, I haven't stuck them on. You totally can stick them here. The thing is, we need to remember that at the end, we have to plug the limits of integration actually into both pieces. So it's not just that it has to go onto the integral. We also have to evaluate this first piece from 1 to 2. So I personally just wait until the very end to take care of the limits of integration. I often don't put them on my middle steps until I need them. But that's a little bit of an abuse of notation. So what we actually end up here with is, I'm going to rewrite the first part. It's x ln x. You can't multiply those x's together because that first x is attached to the natural log, right? So it's not the natural log of x squared. It's x times the natural log of x. And then minus... So in the second piece here, the x's would cancel. So I just end up with minus the integral of dx again. And remember, the integral of dx, we just did it, is x. So we end up with x ln x minus x evaluated from 1 to 2. And now all I have to do is plug in. So we end up with 2 natural log of 2 minus 2 minus 1 natural log of 1 minus 1. Anybody remember what the natural log of 1 is? Yeah, 0. So the natural log of 1 goes to 0. The natural log of 2 is just natural log of 2. It's some ugly decimal, and we're just going to leave it as the natural log of 2. So I have 2 natural log of 2 minus 2 minus negative 1. So we have 2 natural log of 2, and then I have minus 2 minus minus 1. So it's minus 2 plus 1. So it's just minus 1. And so that is my final answer there. Questions? So they're not too terrible yet, right? all of my calc students usually always laugh at me, or I should just say all of my students by the end of the semester usually laugh at me, because I'm always saying, it's not too terrible yet, right? You know, so they're always like, you always say that, and then eventually it gets terrible. But I actually don't think this section gets really terrible. And sometimes I tell you these random stories because I'm trying to give you time to type into the chat box if you... Oh, it's the yet that's scary. Yeah, I know. It's when I add. That's not too terrible yet. But this really, I don't think gets much scarier. So, but yeah, you'll notice that sometimes I am going to just fill time with a tiny bit of random stories to give you guys a little bit of time to put into the chat box a question. I know, it's really weird. It's so weird to teach this way. I don't like it, but it is what it is, right? So you're getting as close to the regular Dr. Gorman experience, all the corny jokes and the stories and all that stuff. It's just that the only person that I can see is myself. So it's kind of, I was joking with one of my girlfriends who I went to graduate school with and saying about how, well, at least when I have my camera on, I can look at myself and I know there's someone who's engaged in the lecture. So, but it's weird. It's like I'm lecturing to myself. So it's very odd. Okay. So should we try another one? You're all like, sure. All right. So let me, okay. So this is,
Hi.
Hi.
Can you, read back the last slide for, 1 second?
Sure.
I just need to write out something.
Sure.
Oh, okay, good. Thank you.
No problem. Okay. So problem C, the integral of r squared plus r plus 1 e to the r dr. Okay, so again, this is, if you look at this, it's not something I just know how to take the integral of. If I tried doing a U-substitution, I'm going to run into problems again. So it's, again, an integration by parts, right? Because I don't have a lot to work with yet. You know, as we go after the first test, we're going to get some more techniques of integration. So we're going to have some more bags or tricks in our bag that we can pull out to use on integrals. But so far, there's really nothing else we can try. So I'm going to start by trying to figure out what my u should be. So if I look at this Laete, right, I don't have a logarithm. I don't have an inverse. But I do have an algebraic function. And so that algebraic function that I have is this r squared plus r plus 1. Oh, no, that's fine. Yeah, if this was a problem on the test and you wanted to rewrite it with x's instead of r's, that's totally fine with me. So we're going to let u be equal to r squared plus, r plus 1. Which then means our dv is e to the r dr. So, questions about how I got that? No. Okay, so just like before, I'm going to do the same thing. I'm going to take the derivative, so du. So the derivative here would be what? Yeah, 2r plus 1. So 2r plus 1 dr. And then v is going to be the integral of e to the r dr, which is going to be just e to the r. And so just like before, I'm going to plug into my formula, right? So, and I'm going to do it kind of underneath this time. So this is going to be equal to, oh, whoops, that's what I probably So this is going to be equal to, so remember the formula, it's uv minus the integral of v du. So it's going to be uv, so r squared plus r plus 1 times v is e to the r, minus the integral of v e to the r times du, so times 2r plus 1 dr. Questions about that step? No? Okay. So, all of our last problems, the last two problems, when I got to this, whoops, thought I hit the pointer, I hit the eraser. At least this is better than on a blackboard, right? But on a blackboard, I probably wouldn't, like, go to point to something and accidentally erase it. But anyway, in the last two problems, when I got to this integral, I knew how to integrate it. But if you look at this is still a mess, right? This is still something I don't know how to integrate, which means I have to actually do integration by parts again. So sometimes you have problems where within the problem you have to do integration by parts multiple times. So we're going to work on just this integral part right here. And we're going to work on doing, I said no out loud. No. Yeah, I'm sorry. Unfortunately, we do have to do it. So we're going to work on just that inside integral again. Okay. So in this case, now, usually, yeah, sometimes you have to do them a lot of times. Those aren't fun. So, well, they're kind of fun. Like, I like them because I'm just like, oh, it's just the same thing. Yeah, this really actually isn't that messy. If you wait till like my last example of the day, which is a little messier, just to put it out there. I know, I'm sorry. So if you remember here, we let u be, we let u be the algebraic function and we let dv be the e to the r dr part. You kind of want to keep the same convention when you're doing that second integration. So here we're going to let u again be the 2r plus 1. We're going to again let it be the algebraic part. And we're going to let dv again be the e to the r dr part. So it's not like dv always has to be the first, or it's not like u always has to be the first thing in the integral and dv has to be the second thing. You can kind of mix and match stuff around. But we're just going to do the same thing again, right? So we're going to let this be, so then we're going to find du. So the derivative of 2r plus 1 is 2 dr. And the integral of v, or dv, to find v, we're going to take the integral of dv. So we're going to look at the integral of e to the r dr, which we said was just e to the r. Questions on what I did so far? Yeah, I should say you just got to get used to the fact that Calc 2 problems are long. They are not usually short problems. Which is why I try to be really, really conscientious in terms of how many homework problems I'm giving you. Okay, so I still have to bring down this part here, right? This is still part, yeah, I always thought calculus was way easier than physics. I did not like physics when I took physics. So we still have to bring down this part, okay? So that part's going to come down. It's staying. R squared plus R plus 1 e to the r. Minus, so I had this pink portion, which was the integral, right? So think about it. I'm going to replace that integral part with a new thing. So it's going to be uv, so 2r plus 1 times e to the r, minus the integral of v du. So in this case, that's going to be e to the r times 2 dr. And remember, it's minus all this stuff. So if I write this down, I really have r squared plus r plus 1 e to the r minus 2r plus 1 e to the r. And then I have a minus here, but it's also being distributed to the minus here. So it's going to be a plus. So plus 2 times the integral of e to the r dr. So I just rewrote that integral a tiny bit. So questions on how I got to that step before we finally finish this problem? No. Okay, so all I have left to do is integrate e to the r, which we've already integrated a bunch. So this is r squared plus r plus 1 e to the r minus 2r plus 1 e to the r plus 2 e to the r plus a constant, so plus c. And that is your final answer. And remember, the cool thing about integration, right, is if you really wanted to, you could check your answer, right? I could take this equation here and take the derivative of all of these pieces. Now, for this piece and this piece, I'd have to use a product rule, but I could do it. I could take the derivative of all this and see that it actually does, in fact, come back to what we started with. So that is the nice part about doing problems like this, that you can actually take the derivative and check your work. Questions?
This might be like a really dumb question, but how did you take out the 2 out of the integral and put it outside?
Yeah, sure. So when I take the 2 out of the, so remember, if you have a constant, if you have, I think I don't know if I said this last time, but in Calc 1, you should have went over, if you have the constant, like if you have c times f of x dx, you can factor a constant out in front of the integral sign and just worry about integrating the function. And so that's what I did there. You're not allowed to pull anything that has an x or a variable out in front for us in Calc 2. I should be real careful about that, because in Calc 3, stuff gets a little weird. But in Calc 2, you can't pull a variable out in front, but you can pull a constant. So that 2 here, this 2 here is just a number that's being multiplied times the e to the r. So if I want to, I can pull that number out in front of the integral sign. Does that help?
Yeah, thank you.
No problem. Okay, if you did that, so if you checked your work, would the c become the dr? Yeah, you could think of it that way. Basically, the derivative of c is 0, right? So the derivative of the c goes away. The dr is really more a function of saying the dr gets paired with the integral, so it's saying integrate this function with respect to r. I know in Calc 1 and Calc 2, right, you don't really think about this because your integral and your variable, like the variable inside your integral and the d whatever match, right? So they just match. You know, I have r's here, I have a dr. I have x's here, I have a dx. When you go to Calc 3, where you begin working in 3 dimensions, this part becomes really important because it actually tells you the order that you have to do things in. And it tells you what you're integrating with respect to. And the reason that is because you're now in 3-dimensional space, so you have to actually kind of think about, well, which direction of space am I working in right now? So when you go to Calc 3, this dr part becomes really important. But right now, it's actually not that important. Any other questions? Why did I think physics was harder than calculus? We're in 2 dimensions in Calc 2. Pretty much almost everything we do in Calc 2 is in 2 dimensions. There'll be a little tiny bit at the end that we talk about 3 dimensions, but it's not really calculus. It's just setting some stuff up for Calc 3. I don't know why I thought physics was a moment. I like that because there's moments in physics and then Anyway, I don't know why I thought it was so much harder. I did, but like if you ask my husband, so my husband's also a mathematician, so he has a PhD in math as well, and he at first went to graduate school for physics, and then he decided to change to mathematics. But if you ask him, he thinks physics is easier than calculus. But I guess I just always liked the math part, and I didn't like to have to try to figure out like the physics part of it. Like I remember in physics in college, like my physics teacher was just crazy. Like he was really hard, and he would give our tests would have, there'd be like 6 take-home problems, and then there would also be 10 multiple choice problems, and you would have a whole entire class period to do these 10 multiple choice problems because they were just crazy hard. And I still remember like the one problem. It's like in an empty room is a refrigerator that is running and the doors are open. Like, is the room getting colder or hotter or staying the same? And I just remember staring at it being like, I have no idea. And eventually I just picked one of them. And it was crazy because I actually picked the right thing. And not only did I pick the right thing, but on that test, I happened to get all the multiple choice ones correct. And like 4 of them were a guess. Every time I took a test, like at least 4 of these multiple choice ones were just a pure guess. But I happened to guess right on all these problems that he actually gave me. I'd lost like 5 points on the like take home part of the test. He actually gave me the 5 points back because he was like so like impressed that I'd gotten all the multiple choice ones. I didn't have the heart to tell him like, hey, I guessed at them. You probably shouldn't have given me those 5 points back, but he did. So, and yeah, and he used to like not like, cause we would get to a point where it was just a calculus problem, and then I could just do the calculus because I was just like, oh yeah, this is a Calc 2 problem. Da, 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 da. And he used to always be like, explain to me what you're doing in the physical world when you're like doing that problem. I'm like, there's nothing. I'm doing a U-substitution. I don't know a physical representation of that. I just know it's a U-substitution and that it works. So, physics and I did not 100% get along. Not that you guys all need to hear that, but I feel like it breaks up class a little bit, right? I mean, in this weird environment we're in here. All right. So, oh, I loved chemistry. Yeah, chemistry was my favorite, actually. In terms of the sciences, but yeah, no, I know that. I know your question, Joshua. I'll answer it in a second. So yeah, I loved chemistry. I took chemistry in high school, and I took AP Chem in high school. And then because I was going for math, I didn't have to take any more chemistry, but I would have liked to take more chemistry. Okay. So yes. So in theory, you could do this multiple times. So in theory, you could do this a lot of times. So, I think probably the most I've ever usually given on a test is like twice, right? Because if you can do it twice, like this problem I just did, then I know you know what you're doing. Twice is what I'm thinking. But in theory, you could do it 10 times, you could do it 15 times, you could do it 100 times, right? It just kind of depends on what the problems are. Okay, should we try another one? D. We are going to do the integral of x squared sine x dx. And then I didn't copy this, right? So let me see if I can do that. Okay. So, again, if I look at this problem, right, I know how to integrate x squared, I know how to integrate sine x, but I don't know how to integrate them when they're multiplied together. Also, there's a key that, I should be able to, okay, that's how I would do it. I thought I'd hit it, but I didn't, but thank you. Excuse me. So it's not just a regular integral that we know. It's not U-substitution. So it's going to have to be integration by parts. And so if I begin to look at the stuff here, I don't have a logarithm, I don't have an inverse, but I do have an algebraic. So we're going to let the algebraic part, that x squared, be our u. So if I let u be x squared, then dv is basically everything else. So dv is going to be sine x dx. And so now, just like before, I'm going to find du and find v. So du, so the derivative of x squared is going to be 2x dx. And the integral of dv, so v is going to end up being the integral of sine x dx. And the integral of sine x is minus cosine x. Questions? Okay, so just like before, I'm going to plug into the integration by parts formula. So we're going to get uv. So I'm going to kind of put those two together, right? So I have u, which is x squared, and I have v, which is this minus cosine x. So rather than write x squared times minus cosine x, I'm just going to put the minus in front. So minus x squared cosine x minus the integral of v, so d times du. So minus cosine x times 2x dx. So I'll rewrite this all a little nicer. So we've got minus x squared cosine x. Minus times a minus is a plus. And I can factor that 2 out to the front. So I have plus 2. And then I'm going to rewrite this second piece again as x cosine x dx. So I did a lot of kind of algebra in that step there, right? Remember the order. If I want to write cosine x times this stuff or times the 2x, I could write 2x times the cosine x. And that's essentially what I did. I flip-flopped these two spots, and then I pulled the minus 2 out in front to get that plus 2. Questions on what I've done so far? No. Okay, so again, x cosine x, it's not something I can integrate. So I'm going to have to do integration by parts again on it. So we're going to have u, again, we're going to let be the x. dv, we're going to let be that trig function part again, so cosine x dx. So du is just going to turn into dx. And v is going to be the integral of the cosine of x dx, which is just sine x. And so now all I have to do is plug in. So I'm going to have minus x squared cosine x plus 2, and then inside this 2, that's where I'm going to put my new integration by parts. So in my new integration by parts, I have uv, so I have x sine x minus the integral of v du, so minus sine x dx. And all I have left to do is integrate that final sine x. So we end up with minus x squared cosine x plus 2 times the quantity x sine x minus the integral of sine x is minus cosine x plus c. So if I clean this up just a tiny bit, minus x squared cosine x plus 2x sine x. So what I'm doing is I'm distributing this 2. It's got to go to this piece. It also has to go to this piece. But over here I have a minus times a minus. So I'm going to end up with plus 2 cosine x plus c. Questions?
Where did the 2x from the cosine come from again?
Where did the 2 at the very end?
Oh, wait, no, never mind. I see. it's from the du, I think.
Oh, you mean here? That?
Yeah.
Yeah, that's from the du. So du is 2x dx. So that's why I needed that 2x dx part there.
Oh, cool. And you just took it out of the...
I took the 2 out, but I left the x in, but I rearranged it and put the x in front of the cosine, right? So,
Okay, cool.
yeah.
Thank you.
No problem. Other questions? No. Okay, so I have one more problem to show you. So that was what, D? Okay, E. All right, so problem E. Oh, sure. Yeah, just let me know when it's okay to go on. Yeah, that's one of the problems with online, right? Because I can't see you guys writing, so I don't know, like, how you're doing. No problem. Okay. So, part E is going to be the integral of e to the 2x sine x dx. Okay, and then, let's see, just paste my thing here in the corner. Okay, so again, right, I don't know how to just integrate this. I can't do U-substitution, so I'm going to be stuck with integration by parts. So if I look at my mnemonic to help me, I don't have a logarithm, I don't have an inverse, I don't have an algebraic function this time, but the next thing I have is a trig function. So we're going to let U, in this case, be the trig function. So U is going to be equal to sine x, and dv is going to be equal to e to the 2x dx. So du, so the derivative of sine is cosine, so this is going to be cosine x dx. V is going to be the integral of e to the 2x dx. I should have, so kind of how I gave you guys the shortcut for, like the sine of AX and the cosine of AX and the last time integrating those, there's a shortcut for the integral of e to the AX dx. So again, it has to just be, yeah, so you could do a U-substitution, or you could use my shortcut, which is if you happen to have just a number in times the x, right? If you were to do out the whole U-substitution, all that's going to end up happening is this is going to be 1 over a e to the ax plus c. So you could, for sure, do out the U-substitution. I'm just not going to because this problem is already going to be long enough. So I'm going to save ourselves a little bit of a step there. And that's why those couple things that I gave, like the ones for the sine and the cosine, and then this one here for the exponential, are pretty helpful. So this ends up being 1/2 e to the 2x. Questions? No? Okay, so I'm going to plug in. So this is going to be uv, so 1/2 e to the 2x sine x. I just wrote instead of writing u first, I wrote the v first, but it doesn't matter, right? It just makes it look a little nicer here. So uv minus the integral of v, 1/2 e to the 2x du. cosine x dx. So I end up with 1/2 e to the 2x sine x minus 1/2 the integral of e to the 2x cosine x dx. Questions on anything I did so far? No? Okay, so just like the last time, right? This is so just like before, this is a, double U-substitution problem. I have to do U-substitution, or not U-substitution, integration by parts again. So on this second part here, again, we're going to let U be the trig function. So U is cosine x. dv is e to the 2x dx. So du, the derivative of cosine, is negative sine x dx. And v is again going to be the integral of 2x dx, which in this case is again 1/2 e to the 2x. So I haven't done anything super crazy yet, right? Like I've just started with what we have. And now I'm going to plug back in again. Right? So I'm going to end up with, I still have this first part, 1/2 e to the 2x sine x minus 1/2. And now I have uv, so 1/2 e to the 2x cosine x minus the integral of v du. So it's going to be 1/2 e to the 2x times minus sine x dx. And before I do anything else, I'm going to kind of clean up what I have. So I have here 1/2 e to the 2x sine x. This minus 1/2 has to get multiplied times this piece and also times this piece. So that first piece is going to give me minus 1/4 e to the 2x cosine x. In the second piece, I'm going to have minus times minus, which is a plus. Again, 1/2 times, oops, actually, I should be careful. So I have minus 1/2, and another minus. So all together, it's still going to be a minus. And then 1/2 times 1/2 is 1/4. And, whoops, then I have the integral of e to the 2x sine x dx. Okay, so before I go any further, does anybody have questions on any of the stuff I did so far? Yeah, it kind of is a loop, right? So some people notice I'm back to where I started, right? I have an e to the integral of e to the 2x sine x. So I was trying to integrate e to the 2x sine x. I did this integration by parts. I did integration by parts again, but I'm back to the same integral I started with, which is, you might think is kind of a problem, but it's actually not a problem. But the reason it's not a problem, I'm going to show you. But it's a little discouraging, right? Oh, I did all this work and I didn't actually get anywhere. I got back to where I started. So I'm going to show you what we're going to do here in a second. It's actually pretty cool. At least I think it's pretty cool. But before I do that, I want to answer any questions about any places where people might have gotten lost as I was going through this, just because it's easier to answer this before we do the next part. So if there's anything I put up there that you don't understand that I did, like definitely ask me a question. It's not a problem. No? Okay, so I do want to take care of the fact that I have a loop. So what I'm going to do is I'm actually going to write down exactly what we have. But I'm going to start with this first part here, right? So remember, we started with this equation. or not this equation, this integral. And now we know that this integral is equal to all this stuff. So I'm actually going to write that down in one line. So we have the integral of e to the 2x sine x dx is actually equal to 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x minus 1/4 the integral of e to the 2x sine x dx. So I basically just rewrote what I have. Okay, good question, Delta. So you're talking about this one here. Why is this one negative? Shouldn't it be positive? Okay, so it's negative because I have a negative 1/4 here. I have a negative here, and I also have a negative there. So I have 3 negatives, and those 3 negatives, negative times negative times negative, is still negative. And then I have this 1/2 and this 1/2, and that's where I get that 1/4 from. Does that make sense? Yeah, it's easy to lose track. I almost put a plus there too when I was writing it. Other questions? Okay, so now all we're going to do is a little bit of algebra. So I'm actually going to take this whole term here, and I'm going to add it back to the other side of the equation. So think about if we were just like moving x from one side of the equation to the other. We can, do it if we, if I had plus 5x on one side of the equation, I could subtract 5x from both sides. So we're going to do the same thing. So I'm going to take that that last integral there and add it to the other side. So we're going to have the integral of e to the 2x sine x dx plus 1/4 the integral of e to the 2x sine x dx. And that's equal to 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x. Does that make sense? I don't really substitute it. All I did was took this whole piece and I just moved it to this side of the equation. So now I've got one integral plus another integral on the left-hand side, and on the right-hand side, I have no integrals. Okay, so now the thing is that you want to notice I have one of these integrals plus 1/4 of these integrals. So I have one of a bunch of stuff plus 1/4 of that same bunch of stuff. So what I really have is 5/4 times the integral of e to the 2x sine x dx being equal to 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x. I'm going to shift this up here a little bit so I have enough room. So I put those two integrals together, right? I have one whole integral, and then I have another 1/4 of that same integral. So all together I have 5/4, right? Remember, 1 is the same as 4/4. So I had 4/4 plus 1/4. That's how I got the 5/4. And remember, I'm trying to solve for this original integral, right? I'm trying to figure out what this original integral is. I almost have it. The only issue is I have this 5/4. So what I'm going to do is to get rid of the 5/4, I'm going to multiply both sides by 4/5. So I'm going to take this whole side and multiply it by 4/5. So we're going to end up with the integral of e to the 2x sine x dx is going to be equal to, so 4/5 times 1/2 would be 4/10 e to the 2x sine x. And I guess I really could actually I shouldn't write that as 4/10, right? The 2 and the 4 would cancel, so it's really 2/5. So 2/5 e to the 2x sine x minus 1/5 e to the 2x cosine x. And now I finally found what that integral is, so I'm going to need to, I'm going to need to add that plus c. Does that make sense? So you might go, well, it seems kind of weird you just added the plus c. Remember, all along the way here when we were doing these integrals, technically we were getting like a plus c hanging around. So that's like, we just are waiting till the very end to put that plus c. So I think this problem is really cool because I integrated something without actually ever really integrating it, right? I did integration by parts, I got back to where I started, and then I just rearranged a bunch of terms, and I figured out what the integral is. And I think that's super cool. I'm sure you guys might not think that's super cool, because you're like, ugh, that's a lot of work. But it's so cool! I didn't actually integrate it, but I figured out what the integral is. And that's just nice. Questions? Yeah, it's really cool. This is why I like Calc 2, right? Calc 2 has some cool stuff. Yeah, it is. It's neat. I like it. All right. Maybe. I haven't written the test yet, so I don't know for sure if I'll put one like this on the test. I have in the past put one, but I haven't. But I've also not put one. Yeah, I mean, I feel like every mathematician's a little bit crazy. We're kind of a crazy bunch. I had someone actually say that to me the other day. It's like, most mathematicians are not like, normal people. And I was like, yeah, that's pretty true. So can I explain again where the 4/5 came from? Yeah, sure. So, I had this 5/4, right? And I want to get rid of the 5/4 because I want to just get down to this integral. So I want something that when I multiply by 5/4, it goes away. So I just basically flipped it. It's the same as if I divided both sides by 5/4, but dividing both sides by 5/4 is the same as multiplying both sides by 4/5. So if I have a fraction and I want to divide by it, it's the same as flipping the fraction over and multiplying it. So that's where I picked this 4/5. So I did 4/5 on this side, which would cancels out the 5s and the 4s, and I'm just left with this integral. And then whatever I do to the left side, I have to do to the right side. So I have that 4/5 on the right-hand side. Does that help? So actually, when you get to get a PhD, so everybody that has, like myself, that has a doctor in mathematics, you actually have to create new math. So there are things in calculus, not stuff that's like going into calculus textbooks, but things kind of behind the scene that are higher level calculus concepts that are still being discovered. My PhD, I did in an area called graph theory, and so I had to come up with a new part of graph theory. And so like when you do it, basically you kind of take stuff that people have done before, and then you're kind of like, oh, I think maybe I could do this one more step. Like I could look at one more thing or look at this a little different and prove something else or come up with a new formula or a new theorem or stuff like that. So yeah, so there still is new math being developed, just like in science, right? They're discovering new things. No, that's totally fine. I do not mind the random questions. So, and most people don't know that that's what has to happen to get a PhD. So that's the difference. Like that's essentially, so anyone that has a PhD in math had to discover some kind of new math. And if you have a PhD in something else, like, so some people have a PhD in math education, or they have an EDD in math, or an EDD in education. So EDD is like an educational doctorate. They also have discovered something new. It's not necessarily a new math formula or a new theorem, but they might have discovered a new way of looking at something, or analyzing something, or teaching something. So basically anybody that has a doctorate that's like in academia, they've done something new, or looked at something new, figured out something new, discovered something new to get that degree. Okay, so the test is next Thursday. So yeah, so let me share my Canvas screen here. I was kind of stalling to give people a minute to finish copying stuff. So I'm gonna stop sharing that. And I'm going to stop this recording.